So Post Quantum Cryptography is a new form of cryptography to that which we use today. And it's based on the idea that in the future there will be something called a cryptanalytically relevant quantum computer. And due to some algorithms that are well established, it's possible that such a machine would be able to effectively break the algorithms or break the ciphers that we use today to protect our sensitive information and our communications. First of all, the release of the new standards has brought the notion of the change to post-quantum cryptography into front and center into the minds of people working in the cybersecurity industry. And there is concrete evidence that nation-state actors have been attempting to steal sensitive data related to government and strategic industries such as the defense complex, healthcare and financial services. And even though that data might be encrypted, at some point in the future, when a cryptanalytically relevant quantum computing resource is available to those threat actors, they could decrypt that data. Increasingly, we're seeing a focus by governments around the world on transitioning their economies to a post-quantum cryptographic state. In fact, in the United States, US federal agencies have to be post-quantum compliant by 2035. And in Singapore, for example, they have the National Quantum Safe Network Plus program that's due to be implemented by 2030. And that interest in transitioning to post-quantum cryptography is cascading down to commercial organizations that know that because they're part of those supply chains, they also need to be compliant. And now that we have standards, they have the opportunity to implement those algorithms, and we're starting to see focus within security teams on undertaking that work. We've been heavily involved throughout the consultation process that NIST in the United States has been running to select post-quantum cryptographic algorithms. Now that those standards are available, we have been implementing them within the software of our Data Security Manager service, and that is available today for customers to implement and test. And we're working to support them in testing with their workloads using these new algorithms. The other thing that we're doing is we're involved in several other initiatives within some key international projects, but we're really now positioned working with industry, academia and government institutions at the forefront of this transition to the new cryptographic environment that will guide us as we move forward. So Fortanix has been a pioneer in confidential computing since its earliest days within industry. We're recognized as leaders in the space. By using our confidential computing technology, which enables you to test the software that you are working with in conjunction with those cryptographic algorithms, and then using a certificated authentication process from that confidential computing environment to the HSM, you can have a complete cryptographic wrapper. And that makes Fortanix quite unique because we can protect data in all three of its phases: at rest, in transit, and in use. Fortanix Data Security Manager HSM technology is built using confidential computing that protects key generation, key management operations, identity and access management, all of the crucial security functions around the management of post-quantum cryptographic keys. And secondly, we can deploy applications using confidential computing so that when you're using post-quantum cryptography, those endpoints where you want to implement the cryptography can also be secured. And that could cover things like the implementation of artificial intelligence, databases, and the types of applications where you're going to be using sensitive data that needs to be protected using post-quantum cryptographic algorithms, and equally the communication pathways between those applications and the hardware security module can also be protected by post-quantum cryptographic compliant TLS 1.3 communication protocol. So I view the transition to post-quantum cryptography as a complex change management problem, and there are two different aspects to solving that problem. The first is that there is a lot of legacy hardware and applications that need to be converted to use post-quantum cryptography because of the additional computational burden that it imparts. And that's going to be a challenge for organizations because some of that legacy hardware is not going to be suited to the use of post-quantum cryptography, and the types of hardware accelerations that might be necessary, particularly within edge devices, for example, are still some way off. So that's why we're encouraging customers to test with the post-quantum cryptographic standards that have now been released with their own workloads. There is benchmark reference data to compare PQC algorithms to the algorithms that we've been using thus far, but it's not really representative in terms of what customers are going to experience in the field. So there's a technical challenge there that needs to be addressed, and customers need to be thinking about the process of understanding their own particular environment, and we can support them with that. The second aspect, though, is really an industrial and organizational change management problem. You cannot transition to post-quantum cryptography in isolation. And for those cryptographic standards to be implemented robustly, everybody needs to be using them within a common framework. And so this is going to be a big challenge in terms of organizations coordinating with industrial standards bodies and within their own supply chains to ensure that the transition happens smoothly, and it's probably going to need to be done on a risk-based approach where the most sensitive data is tackled first, and then the implementation of post-quantum cryptography cascades down to lower level, less important information. So to help organizations plan for the transition to post-quantum cryptography, NIST has published a special publication 1838A, which is currently in draft form, which gives guidelines for migration to post-quantum cryptography. Those guidelines help organizations understand the practices that they need to be following in order to prepare for what is a large-scale change. Fortanix has introduced an important technology called Key Insight, which enables you to understand where your cryptographic keys are currently being used, and then to plan for remediation of those keys to post-quantum cryptographic standards according to a risk assessment process that the customer can conduct. It's likely that in the future new post-quantum cryptographic standards will emerge that are hardened in some way, or that introduce more efficient performance in terms of the overhead and the burden in implementing cryptography. So because the Fortanix Data Security Manager system is software based, it's very easy for us to implement revisions to standards and new algorithms as they emerge, and to adapt to changes in the security posture within the cryptographic community with regard to quantum computing, and for our customers to adopt and implement those changes very rapidly. They're not going to be encumbered by legacy hardware, for example.